Alright, so our conical pendulum. So the sides of the cone, I guess here, the slant edges, really it's basically the string it was hanging on. And the object itself moves in a horizontal circle. Horizontal circle. So the object is moving in circular motion. So let's give our cone some dimensions so we can do some work. So the cone will have a height, a radius, the angle the string makes with the vertical there, that'll come in handy. Right, I'm going to draw all the forces that are happening here. So there's Bob, or the helicopter. What forces do we have? Well, remember we said tension the other day when we talked about string. There's always tension going away from the object up the string. So that's a force in this problem. You'll notice in this case, it's not horizontal, it's not vertical. So we'll end up taking a component like we do in projectile motion. We'll take a vertical component and we'll take a horizontal component. The other force that's there is the force due to gravity. So mg. They're the only forces acting on this problem. So theta, so that's going to be the angle, we need that. And of course omega is the velocity I was rotating the object in. So the angular velocity. So the resultant forces, well, it's circular motion. If I think horizontally and vertically, well, horizontally, it's just purely moving in circular motion. And we know the resultant force of circular motion is the centripetal force. So that'll be horizontally. Vertically, until I sped it up, it stayed at one level. It was only when I increased the angular velocity. So if we're talking about constant angular velocity, it should stay level. So it's not moving up and it's not moving down. So the result of all the forces vertically should be zero because it's not being forced up or down. So horizontally, we'll have our centripetal force. So I put it in terms of linear velocity there, mv squared on r. Vertically, we get my double dot equals zero. So the problem is very similar to what we did with projectile motion, where we said, well, hang on, let's look at what happens horizontally, what's happening vertically. I know all the horizontal forces, the resultant force is mv squared on r. That's what we're basically saying here. And all the vertical forces will sum to give zero. That's what was the idea that I'm going to use for this. So all right, well, I'm going to have to break up tension into components. So if I look horizontally, we have a component of the tension. And if I use theta as my reference angle, it would turn out to be sine because it's the opposite side to the angle. So T sine theta. But there are no other horizontal forces. So I know that T sine theta then must sum to give mv squared on r. If I was using angular velocity, it would equal mr omega squared. Now vertically what's happening? I have a component of tension going up and of course the force of gravity going down. These two must be balanced because we said they're going to add together to give zero. Doesn't really matter which one I make positive because it's equaling zero. So I've defined up to be positive for this one. So T cos theta minus mg is equal to zero. Okay, so we can play with this now. I don't actually need to know the tension in the string if I know the angle. So look, the tensions will cancel when they set up like this, and sine on cos, of course, becomes tan. And so I end up with a little equation here. Tan theta is v squared on rg. So that's a formula I could use to go and solve some problems. If I was working with angular velocity, I'd end up with r omega squared on g. But hang on a sec, I can go even better than that. I don't need to know the angle because we know the radius of the cone and we know the height of the cone. And tan theta would be the radius over the height. So I could substitute r over h in for tan theta. And I end up with the height of the cone being r squared g on v squared. And if I was using angular velocity, very interestingly, it simply becomes g on omega squared. Now g, of course, is a constant. And this backs up what I was saying about what happens when I speed it. Because the only thing that's changing there is the angular velocity. As the angular velocity gets bigger, but it's in the bottom of the fraction, that means the height is getting smaller. The helicopter rises, or the bob rises. So there's some implications we can get just from that one little equation. We know the depth of the pendulum, that's the height of the cone, is independent of the length of the string. You notice nowhere in there am I talking about the length of the string. So it didn't matter how long my string was. If I moved with the same angular velocity, that height of the cone will be the same. Now the radius will obviously be different if the string's longer or shorter if it's, the string's shorter, but the actual height of the cone will be the same. The only restriction, I guess, is it can't be bigger than the length of the string, because that would be impossible. It's always going to be attached and things like that. And as the speed increases, as we just talked about, that means the particle or bob, the helicopter, will rise. Okay, well, let's solve a problem then. So I'm going to get my conical pendulum and I'm going to increase the speed from 60 revolutions per minute to 90. We want to work out, well, how much will it rise? So if this is a fresh question, again, we always start with the forces. So I draw myself up my force diagram. Yes, I've got tension going up the string, force due to gravity, basically exactly what I just did, because every conical pendulum pretty much is the same. I'll put some dimensions in there so I can break up my tension into components. So my horizontal forces I know will sum to give mv squared on r. My vertical forces I know will sum to give 0. So there's good old Bob. We only have t sine theta going horizontally. I'm using mr omega squared this time because they've quoted the question in angular velocity. And vertically, there we go, and t cos theta equals mg. So you'll notice I'm basically doing exactly what I just did in the theory. So tan theta is mr omega squared times 1 on mg. I get r omega squared on g. But hang on a sec, I know tan theta, that's r on h. So now I can get a formula for the height of the bob. I want to know how much it changes. Well, it started at 60 revolutions per minute. 2 pi radians per second, of course. I need it in radians per second, not revolutions per minute. So I sub that in. It's g on 4 pi squared. If I speed it up to 90, which now becomes 3 pi radians per second, we get g on 9 pi squared. So the amount it's risen will be the difference between those two heights, and I think I used 9.8 for g there, I get an approximation of 0.14 of a metre. So 14 centimetres it would have risen. Let's have a look at an HSC one. Now this one was quite interesting because you'll notice here that Bob is actually resting on a cone. So it's a conical pendulum going round a cone. So a different cone itself. So it's attached to the string. Now, the angle of the cone, they've told us, is 2 alpha. The angle the string makes, well, they've actually given us the angle it makes with the horizontal rather than the vertical there, but it's still the same idea. It's alpha. Now, this normal reaction, what on earth is the normal reaction? Whenever your object is making contact with a surface, there will be a resistive force in the opposite direction. Again, it's like me standing here on the ground. Yes, gravity wants to pull me down, but there's a resistive force going back up so that my legs aren't collapsing. There is a normal force also acting on me, the ground acting on me. So that's what this N force is here. Because Bob is on the surface of the cone, it's touching a surface, so therefore there will be a normal force going away from the surface at right angles to the surface. So whenever a particle makes contact with a surface, we know we're going to have that resistive force, that normal force, perpendicular to the surface. Show with the aid of a diagram that the vertical component of that normal force is n sine alpha. So all right, there's Bob. What did we have? Well, we have tension going up the string. We've still got that. And that will be broken into components. Now, they told me alpha was the angle with the horizontal, if you like, the angle of depression. But so I can get that angle into the triangle. Angle of depression always equals angle of elevation, alternate angles. So I know alpha is down there. We also had this normal force. Now, how to resolve that into components? Well, again, we'll have to go vertical and horizontal, but how do we get alpha into this diagram? Well, let's go back to the original picture they gave us. Remember, Bob was sitting on a cone, and they said the angle was twice alpha. So if I just draw a vertical in, that bit there would be alpha. If I play around with it, well, that's got to be alpha then because of alternate angles. The vertical's going to be straight up. Remember we said the normal force was at right angles to the surface. So this angle here next to alpha must be 90 minus alpha, which means alpha must be the other one in that triangle. So I now can resolve the horizontal and vertical forces of the normal, and in fact they want us to do the vertical component. We're using that triangle. All they're interested in is the vertical component. I'll call it C for component. And if I look at that triangle, I can say, oh, well, C over n sine alpha. So sure enough, that component is n sine alpha. That's what they wanted me to show. And I guess they're probably more interested in your force diagram there and how you worked out where the angle goes and things like that. Okay. Part B of the question then was, well, all right, if you add these two forces together, the tension and the normal force, show it's going to be mg on sine alpha, and then find an expression for the tension minus the normal force. And they want that in terms of the mass, the length of the string, and the angular velocity. Okay, horizontally, it's still circular motion. It doesn't matter that it's sitting on a cone. Still circular motion. So I know horizontally all the forces will be mr omega squared. So there's Bob. Horizontally, we've got a component of tension going to the left and a component of the normal force going to the right. Now, which way is positive? Well, towards the centre of the circle. Remember, the resultant force is always towards the centre of a circle. So that would be to the left in our picture. So the T cos theta will be positive, but the N cos, well, call it a theta, sorry, alpha. And the n cos alpha will be negative. Okay, I'll do a similar thing for vertical. Now, if we look at vertical, I've got a component of tension going up. I've got a component of the normal force going up as well. But I also have this force due to gravity. They will all add together to give 0. And once again, it doesn't really matter which one I make positive and negative in this case because they're going to add to 0. I made up being positive, so T sine alpha plus n sine alpha minus mg is 0. And I've just rearranged that to get T sine alpha plus n sine alpha, because remember, we're trying to get an expression here for T plus n. And you say, well, now all I've got to do is divide both sides by sine alpha, and I've got it. So T sine alpha plus n sine alpha is mg. Divide through by the sine alpha. Okay, we've got the expression they asked for. Now, T minus n. Well, I can do a similar thing. T cos alpha minus n cos alpha is mr omega squared. Divide by cos alpha. However, they said in terms of mass, I've got that. Length of the string, haven't got that. And what was the other bit they wanted? Angular velocity, well, I got that. So the r and the cos alpha I'm going to need to get rid of. Well, if we have a look at that triangle, the radius of the conical pendulum over the length of the string would be cos alpha, adjacent over hypotenuse. So in other words, I can just simply substitute in the length of the string for r over cos alpha. And so there's T minus n, ml omega squared. Okay, we're going to increase the velocity, and we just saw that when we increase, Bob will rise. It's going to keep going until n equals 0. That instant that n equals 0 means it's no longer in contact, because there is no normal force anymore. So we're going to speed up, speed up, speed up, and eventually it'll lose contact, because the Bob will rise, it'll come off the cone. It wants to know at that point. So when n equals 0, so the particle just loses contact with the cone, now find an expression for that angular velocity when that happens. So right, n now equals 0 as far as we're concerned. So going back to the two equations we just worked out, I've now got an expression for tension, mg on sine alpha. But I've got another expression for tension, ml omega squared. It's like simultaneous equations now. I can eliminate the tension. I don't need to know the tension. I'm trying to find angular velocity, so I want to make omega the subject of all this. So omega squared will be g on L sine alpha. So that angular velocity is the square root of g on L sine alpha. They've said to do it in terms of alpha LG, so fine. I've got it in terms of what they want. I don't have to do any more substitution. I've got the answer that they were looking for. Okay, so 9B in Cambridge and 9C in Patel are all on conical pendulum. But the key is set your force diagram up. Once you've got your force diagram, just like we did in projectile motion, we can then go, okay, here's my accelerations, and I can play with whatever they ask me.